Hello, we're going to do lesson 15, 8M7 lesson 15, that is the Pythagorean Theorem revisited. This is a lesson where we do a proof of the Pythagorean Theorem, which we've done a couple times this year already, and I'll point those out to you where we've done those here in a second. So let's get on to our drawing pad, and let's talk about what we're going to do. We're going to do the two proofs that you did in class today, the same. They're actually kind of the same proof, but maybe you'll see why. I'm not going to get into how they're the same. Anyway, one's kind of more algebraic, one's a little more visual and geometric. Now notice we've proved the Pythagorean theorem twice. We've done it once in 8M3 lesson 13, and we've done it once in 8M2 lesson 15a. So you can go check out those videos for proofs. The one we do today is very similar, or I mean, almost exactly the same as this lesson 13 one, but it maybe does it slightly differently. It's based on the same principles. At any rate, let's get on with it, and let's move into the two proofs. So both proofs are based on the concept of using similar triangles. So here, the whole idea, we got this triangle, and we have this right angle in it, and we have these vertices A, B, and C, and we have these sides that are opposite these angles. And we'll just make this angle be angle 1, and this be angle measure 2. And then this is a right angle. So, side B is opposite angle B, side A is opposite angle A, and side C is opposite the right angle. Also known as the hypotenuse. C is also known as the hypotenuse being opposite the right angle. So the first key thing that we do in this proof is we create another triangle, and we do it in such a way that we take a right angle straight up. Well, let's do it like this. Let's do a straight line, and we're going to make it straight like that. So now what we've drawn another right angle. We've drawn a line such that this is a perfect right angle, and we can even make that a little bit thicker to really highlight what we're doing here. Let's do this. Right. Okay. So now we have actually three triangles. We have a big triangle, and then we have two little triangles. So here's our big triangle on just, ABC. Then we have triangle ACD, and then we have triangle DCB. Okay, and now the interesting thing to notice is that these are all similar triangles. And we do this proof again in 8M3 lesson 13, where I go on to really explain to you and highlight how you can show that these angles are the same. Angle A and angle DCB have to be the same angle, and then angle ACD, this one, and angle B have to be the same angle. And I'm not going to go into the full-on proof of that. Again, here's the proof that angle A is congruent to angle DCB, and angle B is congruent to angle ACD. Okay. So now what I'm going to do is I'm going to take these three triangles, and I'm just going to draw them down here so that you can really see their congruent, or their similarity, right? Because if this angle if triangle DCB has an angle 1 and an angle 2, and that angle 1 and that is congruent to this angle A, and this angle 2 is congruent to this angle B, then these are similar triangles. And we do a whole unit on that, and that's one of our key building blocks. So let me redraw triangle ADC here. So we'll go A. Here's triangle. You know, pretend those are straight lines. A, D, C. And if we do that, right, side AC, this is B. Okay? Now let's draw this triangle here, and we'll draw it, you know, so that it's, and let's do this. There's angle 1 and there's angle 2. Now let's draw this other triangle that's similar. And this is triangle, this one, right here. So here's our D, right? And here's our C. And here's our B. So side BC is A. Like that. Now we're going to draw the big triangle. And that's just the same as it is right there. Same orientation. I didn't have to twist it around or anything. Let me draw these angles in. And then here we go. This is a B, and this is an A. Okay, and this is side B, and this is side A, and this is side C. So you should be able to see that that's this triangle. I just drew that one down here. And then this triangle is this triangle right here, but I've twisted it and then reflected it. And then this triangle is this triangle here, where I've twisted it and I've rotated it and then reflected it. Okay, so you can see now that these are all similar triangles. And now the properties of similar, now I'm going to use the properties of similar triangles to show you something very interesting. But the first thing I'm going to do is I'm just going to label 2 more sides, and I'm going to use a different color here. So I'm going to say that this whole side here is C. Right? That whole side is C. But I'm going to call this thing here, this side here, X. And so if I say that that's X, then if that's going to be this side here on this triangle, right? Because if this is triangle ADC, then I'm going to say X, X is equal to AD. X and AD are the same thing. And similarly, I'm going to come in here and I'm going to say this side here is Y. So I'm going to say Y is equal to BC. So if Y is equal to BD, BD is Y, so that's here, right? Okay, so I can do, let me see, this is a little messed up right here. Let's get that piece off. So that's our D. Okay, so now here's where the cool thing about the proof comes in. I'm going to use my properties of similar triangles to show you some relationships that have to be true. Now, the key thing when we talk about similar triangles is the ratio. The key thing about similar triangles, I'm going to remind you, this is a building block, is that the ratio of corresponding sides, the ratio of corresponding sides is constant. So if I take this side B and I divide it by this same corresponding side C, so if I say B over C, that's got to be the same as X over B. Okay, so I'm going to just erase those for a second. So B divided by C, the length of B divided by C, that's the corresponding side. It's got to be the same as X divided by b. That has to be true if they're similar. Now I'm going to do a similar thing using these two triangles. So what would I say? I would say, well, A over C is equal to y over A. I can say that. This divided by this, the corresponding side, is equal to the corresponding side, the ratio of these two corresponding sides. And this is where my whole proof comes together. So now I can rewrite this. I can use cross multiplication, and I can say, well, b squared equals x times c. And then I can say, I can divide both sides by c, and I can say, well, x is equal to b squared over c. So I'm going to stop right there, and then I'm going to rewrite this one in the same way. So I'm going to say y times c equals a squared, and then I'm going to divide both sides by c. And I'll say y equals a squared over c. And I'm actually almost there on my proof. Almost there. Okay, now the last piece of information is what? What did I do up here? What cool thing did I do? Or what can I say? Well, I can say that x plus y has got to equal c. Because my x, this length here, plus this length here equals c. So let's write that out. X plus y equals c. That's got to be true. So now let's do substitution. Well, I know that x is equal to b squared over c. So I'm going to substitute that right here. I'm going to say b squared over c. And I know that y is equal to a squared over c plus a squared over c equals c. And I'm almost there. Almost there. That's by substitution. Now what I'm going to do is I'm going to use the multiplicative property of equality and multiply both sides by c. If I multiply this by c, I use my distribution. C times b squared over c is b squared. C times a squared over c is a squared. And c times c is c squared. So I have proved it. I have proved that if we have a right triangle, we can create some similar triangles to show that the square of the sides is equal to the square of the hypotenuse. It's a lot to wrap your head around, but we have used so many building blocks here. We've used our principles of, let's write out some of our building blocks that we've used. We've used our principles of similarity. We had to learn about similarity. We had to use substitution. We had to learn, and we had to use our, our building block of, distribution. And then our multiplicative property of equality. Probably some other things we had to use here. This principles of similarity comprises a lot of different things where we had to talk about congruent, had to prove congruent angle. Triangles are similar if they have three congruent angles. Other principle being the ratio of corresponding sides is constant in two similar triangles. We had, the concept that if you have a straight line and you have a midpoint or some point in between them, that the length of the two smaller sides added together equals the length of the whole. Lots of stuff built up in this proof of the Pythagorean theorem. So let's go now to a proof that's actually kind of the same proof, but it's visually very visually different. This one's more visual, but it actually pretty much uses those same principles. Now, here's the idea, is that if this side, okay, so let's forget about the x and y for a second. Let's just, this side is, if this whole side here is C, and this side here is C. I'll erase this in a second. And the idea is, if a squared plus b squared equals c squared, then this square is going to be a square built off of the side of the hypotenuse. And so the area of this is c squared. This whole thing here is c squared. And if we build a square off of this side, this whole area is a squared. And then similarly, if we do it off this leg here, this area here is b squared. So the idea would be, if we can take the area of this b squared and the area of a squared, and we add them together, a squared plus b squared, then that should be the same area as this big square. So that's the idea of this proof. And now the neat thing, so let me just erase a lot of this. So get the clutter out of the way. Get the clutter out. Now the neat thing about this is that it turns out that this rectangle, if we build this dotted line like we did on the last proof, such that that's a right angle, then it turns out, and we build our side here, x, it turns out that the area of this long, skinny rectangle is the same. These are the same. And it turns out that these two are the same. So in other words, if I take this, if these two are the same and these two blue pieces are the same, then it turns out that if I add this together with this, I get this plus this. And so then this square plus this square has to equal this big square, right? If this is, if this is b squared and this is a squared, then this must be b squared and a squared if they're the same. And so a squared plus b squared equals c squared. So that's what we're going to try and show here. Okay, so I'm going to try to show to you that this thing here is a squared. That's the first thing I want to do. That rectangle I is equal to a squared. And then I want to show you that rectangle 2 is equal to b squared. And if that's true, then rectangle 1 plus rectangle 2 is clearly equal to c squared, because this is c and that's c. So that's c squared. So then by substitution, a squared plus b squared equals c squared. That's another way of saying what I was trying to say here with all of that drawing. Okay, so we're going to erase all this for a second. We're going to erase all this permanently. And how do we go about proving this? Well, so we all we need to do is we're just going to try and show that these two are the same, that 1 is equal to b squared. Well, this square here is clearly b squared. This side is b and that side is b. Now what I want to show you is that this thing here is equal to b squared. Well, how do we do that? We're going to go back to our similar triangles. And so here they are drawn again. This is the, let me go ahead and relabel these guys. A, B, C, and D. So this here is triangle, this is our D. This is this triangle here, redrawn. And this is our A. And this is our C. Okay, and over here, This is our D. And this is our B. And this is our C. And here, this is our triangle. This is our A. And this is our C. And this is our B. Okay. All right. So remember, X over B. So X to B is the same as B to C. These ratios, if I divide these sides, they have to be constant. And similarly, if I take my Y over my A, that's got to equal my A over my C. But remember, if we rejigger this thing by multiplying around, X is equal to B squared over C. And here we get Y is equal to A squared over C. And we did that on the last slide. I showed you how to prove that. You do cross multiplication, and then you do one division, and you get to this point. And here, if we cross multiply and do one division, we get to this point. Okay, so now, what is the area of this rectangle? Well, the area of I is equal to length times width, which is equal to C times X. Well, X is equal to B squared over C. So C times B squared over C. Well, the C's here cancel, and so we get B squared. So the area of I is equal to B squared. So we've shown that these two are equivalent. Very cool. Let's do the same thing here. The area of 2 is equal to the length times the width, which is equal to C times Y, right? Here's Y, and here's C. So that's equal to C, and if Y is equal to A squared over C, we can do our substitution, and we can cancel our C's, and we get A squared. So this is equal to A squared. So clearly, B squared plus A squared, if B squared is the yellow and A squared is the blue, clearly A squared plus B squared is the area of that square, but so is C squared. So A squared plus B squared equals C squared. So that's kind of the visual proof of what we did on the last slide. And again, what were our building blocks? Our building blocks were the knowledge. It was very important to have a knowledge of similar triangles so that we could build these two ratios, these two proportions. Then reworking the proportions, and then just simply using our knowledge of geometry to say that two rectangles laid side by side must be the same area as the whole rectangle, which is, in this case, happens to be a square. Okay, so hopefully you learned something there. Hopefully this was a good exercise, a good proof, a reminder of what we learned in 8M3 lesson 13, and another way of looking at 8M2 lesson 15A. And we will be moving forward with lesson 16 in our next video coming up soon. So enjoy. Hopefully this is fun. You know, some people like to do a lot of calculation. Some people like to understand proofs and concepts. This was definitely a proof and concept type lesson, but it's one of the standards that you should know coming out of 8th grade math. See you next time.